This slide introduces Section 9, which covers quality management and Six Sigma in production. We begin with Chapter 9.1 Fundamentals of Quality Management, focusing on how quality principles support production excellence and CPIM concepts. This slide defines what quality means in production. Quality simply means meeting or exceeding customer expectations by delivering products that are fit for use, defect-free, and consistent. Experts define quality slightly differently. Crosby focuses on conformance to requirements, Deming emphasizes predictable uniformity at low cost, and Huron highlights fitness for use. This slide explains the 8 key dimensions of product quality. Each dimension reflects a different way customers judge quality. Performance is how well the product works, reliability is how consistently it performs, and conformance is how closely it meets specifications. Durability shows product life, serviceability is ease of repair, and aesthetics covers look and feel. Perceived quality depends on brand reputation. Together, these help companies design and measure quality effectively. This slide highlights ways to continuously improve capacity, reducing setup time using SMED, improving availability through preventive maintenance, increasing flexibility with cross-training, and using data-driven dashboards. The Tata Motors case shows how OE monitoring and Kaizen improved efficiency from 78% to 88% without extra capital. This slide introduces Statistical Process Control, or SPC. SPC uses statistical methods to monitor and control processes so they stay stable and consistent. The main goal is to detect variations early before they turn into defects, allowing proactive correction and better quality performance. This slide highlights ways to continuously improve capacity, like using SMED to reduce setup time, preventive maintenance to boost availability, cross-training operators for flexibility, and using IOT dashboards for data-driven decisions. The Tata Motors case shows how OE monitoring and Kaizen increased efficiency from 78% to 88%, adding 10% extra capacity without new investment. If you want, I can also prepare ultra-short one-liners, detailed speaker notes, English speaker notes, PDF of all notes combined. This slide introduces control charts, which help us differentiate between normal variation and variation caused by specific issues. Common charts include XR for variable data, P, and P for defect rates, and C charts for defect counts. Control limits are set at mean plus or minus 3 sigma to identify out-of-control points. The Coca-Cola case shows how SPC reduced overfill losses by 2.5%, saving nearly 50 lakh annually. Process capability tells us how well a process can consistently meet specification limits. CP and CPK are the key indices. CP measures potential capability, while CPK accounts for centering. If CP is below 1, the process is not capable. Values above 1.33 indicate a capable process, and CP of 2 or more is considered world-class. This example shows how to evaluate process capability. With a specification of 500 mm and sigma equals 0.5, the CP value is 1.33, meaning the process is capable. But if the process mean shifts to 49, the CPK drops to 0.67, indicating the process is off-center and no longer consistently meeting specifications. This slide explains how to improve process capability. We can center the process to remove bias, reduce variability using Kaizen, TPM, or Six Sigma, and upgrade equipment or methods when needed. The Bosch case shows how SPC combined with CPK monitoring helped them achieve extremely high precision 99.99% conformance in fuel injectors. Root cause analysis helps identify the real reasons behind process problems so we fix the cause, not just the symptoms. We use common tools like 5 whys, fishbone diagram, Pareto analysis, and FMEA to systematically trace issues, analyze patterns, and prevent recurrence. This slide shows an example of a fishbone diagram used to identify causes of high defect rates. The categories include machine, method, material, manpower, measurement, and environment, each listing typical issues like wear and tear, poor sequence, inconsistent suppliers, inadequate training, wrong calibration, and environmental factors. The example at the bottom explains how using fishbone plus 5 whys helped a packaging plant find the root cause of seal leaks, a temperature control malfunction in one sealing machine. Pareto analysis shows that 80% of problems come from 20% of causes, so we focus on the vital few issues that create the biggest impact. The example from Hindustan Unilever shows how using Pareto plus 5 whys on labeling defects helped reduce customer complaints by 70%. This demonstrates how targeting key contributors drives major improvement. Topic 1. What is Six Sigma? Six Sigma is a data-driven methodology that helps reduce defects and improve processes. It uses statistical tools to understand variation and eliminate errors. Goal: the aim is extremely high performance, fewer than 3.4 defects per million opportunities. DMAIC framework: Six Sigma follows the DMAIC cycle: define the problem, measure the current performance, analyze to find root causes, improve the process, and control to maintain results. This ensures improvement is both structured and sustainable. This slide compares Lean and Six Sigma. Lean focuses on speed by eliminating waste and improving flow. Six Sigma focuses on reducing variation and defects using statistical tools. Lean tools include 5S, Kanban, and VSM, while Six Sigma uses DMAIC, SPC, and hypothesis testing. When combined, you get Lean Six Sigma, fast processes with high quality. Example: a food processing line improved throughput by 25% using Lean and reduced variation by 40% using Six Sigma. This slide highlights the real-world impact of root cause analysis and Lean Six Sigma. By applying structured problem-solving, organizations achieve shorter lead times, fewer defects, and measurable cost savings. The case study from GE Aviation shows how Lean Six Sigma saved them over $1 billion annually by reducing scrap, improving maintenance, and cutting cycle time.